Well, hello everyone, and welcome to today's Nano Exploration Seminar. I'm Bob Atkins. I'll be your host for today. We have Rachel Morgan, who's going to talk about Midwave IR integrated photonics, and it should be a great talk. Before we get started, as usual, a few housekeeping things. First of all, just remind everybody that the seminar is being recorded. And also, in terms of questions, we will have a Q&A period after the talk. So if you could please hold your questions until then. And then you can either put them in the chat, or you can raise your hand, or you can simply unmute and yell out. That usually works just as well. So we'll have that Q&A session at the end of the talk. Jumping right into things, today we have an interesting talk on Midwave IR integrated photonics. So as most of you, I'm sure, are well aware, integrated photonics is fantastic at miniaturizing optical systems, but a lot of that work has been focused on telecom bands, 1.5 micron. What do you do if your optical system is at another wavelength because it's designed to do sensing or something that requires a specific wavelength, and it doesn't happen to be in that telecom band? A lot of the current integrated photonics simply will not work. An example of that is at Midwave. And so today we have Rachel Morgan. Rachel's a PhD candidate in the Aero department. But she's also been working for the last 2 to 3 years with us up at Lincoln Laboratory, and in fact has recently received the Carl Nielsen Scholarship here at the laboratory. So that's fantastic. And Rachel's going to talk today about this case of the Midwave. How do we extend integrated photonics to make it work for Midwave IR applications? So with that, Rachel, if you're all set, why don't you take it away?
Awesome. Thank you so much. Hi, everyone. My name is Rachel Morgan. As Bob said, I'm a graduate student in the Aeronautics department, and I work on integrated photonics at Lincoln Laboratory. I'm super excited to be here today talking about a Germanium-on-Silicon integrated photonics platform for the Midwave infrared. So today I'm going to start with a brief introduction about what integrated photonics is and why we want it at the Midwave infrared wavelength range. Then I'll talk about our progress in waveguide design and fabrication. I'll summarize some of our recent laboratory results, and I'll finish up by talking about some upcoming designs and our plans for the future. So first of all, what is integrated photonics? Integrated photonics applies the benefits of nanofabrication technology to optical devices. It's analogous to integrated electronics, which combines many electronic components into a common substrate for an integrated circuit, which has enabled the drastic miniaturization of electronic devices in the past couple of years. Integrated photonics combines multiple optical components on the same substrate. So over here, we have a little diagram that shows some of the different types of components that we'd want to integrate in an integrated photonic circuit. One of the most important components is a waveguide. Waveguides are like wires for light, and they route the light all around your integrated photonic chip to all the different components. Some other components you'd want to include are filters, couplers, and also active components such as modulators, detectors, and laser sources. Integrated photonics can be used to drastically miniaturize optical devices. Here's an example of that on the right. So this is for a different project at Lincoln Laboratory, where they have an ion trapping beam control system that requires many wavelengths of light to be routed in a small area. The free space version of this setup takes up an entire optics bench, but using integrated photonics to route the light, they are able to miniaturize this whole system into a device about the size of a quarter. There are other benefits of integrated photonics as well. By monolithically integrating many optical components on a common substrate, it is a lot more robust to mechanical vibration, because you no longer need to maintain alignment between discrete free space optical components. Another benefit is that manufacturing becomes highly scalable because you're using batch manufacturing techniques, analogous to integrated electronics. So why do we want integrated photonics in the Midwave infrared wavelength range? The Midwave infrared wavelength range, which we define as 2 to 5 microns, has a number of really interesting applications. So this wavelength range is just beyond the near infrared wavelength range, where a lot of photonics development happens in the telecom band. In the Midwave infrared wavelength range, there are a number of interesting molecular absorption features, shown in this plot over here. These are really useful for remote sensing. For instance, you can measure different absorption features of atmospheric gases to keep track of their concentration. It's also interesting for chemical sensing. There's also an atmospheric transmission window in the midwave infrared wavelength range, which allows for low loss transmission of signals through the atmosphere. There are a lot of different applications that could benefit from the miniaturization and scalability of integrated photonics. For instance, in remote sensing, you could miniaturize the components that you use to monitor greenhouse gases. Having smaller components allows you to save space on a satellite platform, for instance, and to allow more complex components to be included on small space or air-based platforms. However, most mature photonics platforms contain materials. Most photonics development happens in the Silicon-on-Insulator platform. So this is a platform that is developed for the near-infrared wavelength range for telecommunications applications. The insulator, so the I in SOI, actually becomes absorbent past about 3.7 micron. So to allow integrated photonics to happen in the midwave infrared wavelength range, we need a different materials platform. The goal of this project is to enable integrated photonics to be used in the midwave infrared wavelength range using a Germanium-on-Silicon devices. And the goal is to miniaturize optical devices for remote sensing and other applications. So why did we choose germanium for this project? We are developing germanium waveguides with silicon top cladding because these materials are both CMOS compatible. This means that we can take advantage of the very mature and highly precise manufacturing tools that are used in integrated electronics development. These materials are both transparent in the midwave infrared and beyond. So over here is a plot of the transparency windows for various materials in the midwave wavelength range, and it's overlaid on top of the atmospheric transmission spectrum. So you can see there's a lot of interesting features between 2 and 5 micron shown over here, and germanium and silicon are both comfortably transparent in this wavelength range and a little bit beyond. Germanium also has active material properties similar to silicon. So this allows us to design integrated modulators, which is very important for a photonics platform. Using silicon top cladding is going to enable us to design devices that are more robust to environmental conditions. So they're less sensitive to humidity and gases in the atmosphere or in the air. They're less sensitive to the environment that they're in. Including a top cladding also enables easier active component integration. There are a number of materials options that have been considered for midwave infrared integrated photonics. As I mentioned before, the Silicon-on-Insulator platform can work up to about 3.7 micron, but beyond that, the oxide starts becoming absorbent, so you have too much loss. One solution to this is suspended silicon, where you etch away all of that oxide. However, this leaves you without any cladding on top or bottom, so you're very sensitive to your environmental conditions, which is desirable for certain applications, but not for all of them. Other materials considered are silicon nitride, sapphire, and lithium niobate, but these are only transparent up to about 5 micron. So using germanium and silicon allows us to potentially expand to longer wavelengths in the future. Another promising option are chalcogenides, which can give very good performance, but unfortunately this material is not CMOS compatible, so fabrication is a little trickier. Midwave infrared integrated photonics is a very active and exciting area of research. There have been a variety of waveguide and passive component demonstrations in recent years. The most relevant one for this project is a Germanium-on-Silicon waveguide demonstration that was able to reach 0.6 dB per centimeter loss. Most of these components that have been demonstrated in the literature do not contain a top cladding, so they are more sensitive to environmental conditions and less robust. And there have been very few active integration examples in this wavelength range, and even fewer complex systems that combine active and passive components into a full system design. So the goal of this project is kind of build up from low loss waveguides and active device and passive device component demonstrations into a more complex system in the future. Next, I'll talk about our progress on waveguide design and fabrication. Waveguides are a fundamental building block in photonics. They are like wires for light, so they are used to route the light on your photonic integrated circuit to all the different optical components that you have integrated. We use a commercial mode solver to design our waveguides, so you input a refractive index geometry, and it calculates the optical modes or the shape of light that are supported and can transmit through these waveguides. For our design, we assumed germanium refractive index guess based on literature values. We have two different kinds of waveguides on our Germanium-on-Silicon platform. The first kind is a rectangular waveguide, which, like it sounds like, is a rectangle. So it's a single layer of germanium material that confines the light in this high refractive index core surrounded by either air or silicon cladding. These waveguides are highly confined, which means that they can have a tighter bending radius, which allows for more compact routing of light. compared to rib waveguides. Rib waveguides confine light underneath a thin germanium rib on top of a wider germanium slab. So these waveguides are less confined, so you can't bend them as much. However, they do enable more interaction between adjacent components. So these are very useful waveguides for coupling between different components. They also keep more of the light in the germanium compared to the rectangular waveguide, where some of the light kind of leaks around the edges. So these can have lower loss because there's less interaction between the light and the material interfaces at the edges. So we had our first mask tape out in winter of 2021. So here's a screenshot of that first mask that we put together. This first set of devices contain a number of components for measuring waveguide loss. They also contain test components for input-output tapers, bending loss test structures, waveguide type conversion tapers, and ring resonators. The goal of this first set of devices was to measure the waveguide loss and passive device performance with different fabrication approaches for germanium feature definition and for different top claddings. Now I'll talk a little bit about our fabrication flow. Our devices are fabricated at MIT Lincoln Laboratories microelectronics lab on 200mm silicon wafers. We epitaxially grow our germanium using a group 4 ASM reactor, and we have 2 different etch steps for half and full height feature definition. And a big part of this project is experimenting with different top cladding approaches and testing out how they perform in the lab. The first step of our fabrication flow is to grow 1 micron of germanium. We first deposit an oxide hard mask and pattern the resist waveguide features, and then do the first etch, which etches down to 500 nanometers half height features. Then we add some more oxide and pattern the ridge resist pattern, and etch away the oxide in 500 nanometers more germanium down to the silicon substrate. At this point, we can leave the waveguides as air-clad for air-clad samples, or we can deposit a top cladding over top. After that, we etch away these trenches for edge coupling of optical fibers, and then we dice them, and the samples are ready for testing. Here are some pictures from our fabrication development. We see very high quality germanium growth using our ASM reactor. One of the challenges that we've faced has to do with etch byproducts. So during an etch, some of the material is kind of floating around and would deposit on the corners of our devices, shown here. This is sort of a problem because it leads to shapes that are not what you designed. So you don't really know how your light is going to interact with these weird shapes that you see in your devices. In order to get rid of this problem, we experimented with different plasma and chemical cleaning. This was complicated by the fact that germanium is very sensitive to chemical attack. And so that complicated the cleaning options that were available to us. So it took a couple of iterations to figure out a good recipe in order to achieve these 2 etch steps without seeing these features. In the end, though, we have 2 consecutive etch step processes developed. And so we can reliably etch half and full height features without this edge fencing. So here you see a fabricated image of a rib waveguide. Here's a rectangular waveguide. Here's a top view of a fabricated chip. And here's a line width experimental section of the chip. So you can see that our minimum feature size is about 300 nanometer spacing between adjacent waveguides. One of the main goals of this project is demonstrating germanium waveguides with a top cladding, because this reduces your sensitivity to environmental conditions and allows for more active component integration. We have different types of top cladding that we've tested. So here's an example of epitaxial silicon top cladding. Here's an example of LPCVD polycrystalline silicon top cladding. And here's a picture of LPCVD amorphous silicon top cladding. And we use laboratory measurements to kind of decide between these different approaches and choose the most promising one. We've seen a number of different issues in developing this top cladding. One of the issues was germanium mass transport along the surface, kind of seen as this like leakage of material over here and this weird like smoothing out of the shape up top. This is a problem because it leads to waveguide shapes that are not what you designed. And this was alleviated by reducing the silicon growth temperature. So reducing that growth temperature prevented this leakage, and now we get much better shapes in our fabrication. Another issue is polycrystalline silicon showing up in our epitaxial silicon cladding growth. This isn't necessarily a problem, but we're worried that this extra shape and structure here could cause extra scattering and potentially be a source of loss. So we're experimenting with different epitaxial growth conditions to try to mitigate this. Another issue was surface roughening during the silicon top cladding growth. This is an issue because the germanium is actually getting attacked during this growth. And so you see these little mouse bite features This causes extra roughness and would be a huge source of loss. So we do not want our waveguides to look like this. We want very smooth, clean waveguides that do not have extra interaction with the light as the light is transmitting through it. This was mitigated with careful cleaning of the samples prior to top cladding growth. Another issue was keyhole formation. So this happened when we are depositing silicon top cladding between two very closely spaced waveguides. And this is a tiny air gap bubble that kind of gets trapped in there. This isn't necessarily a problem, but this leads to coupling between the waveguides not being what you predicted. So we alleviate this by limiting our waveguide spacing for silicon clad samples to about 500 nanometers for half height features and 1 micron for full height features. So in summary, here's kind of a summary slide of our fabrication status. At this point, we have reliable and repeatable recipes for 2 germanium etch steps with and without edge fencing. We're also developing epitaxial silicon top cladding and experimenting with other top cladding options with lab testing. So here's a picture of an air-clad germanium rib waveguide. Here's a picture of an epitaxially silicon-clad rectangular waveguide and an epitaxial silicon-clad rib waveguide. Next, I'll talk about some of our laboratory results. Here is a diagram of our test setup. So we couple light from a laser into an input fiber. This fiber is then edge coupled, so it's lined up really carefully to the edge of the chip where the light goes into a waveguide. That waveguide routes the light to the device you're trying to test. And then at the output of that device, another waveguide sends the light into an output fiber, which sends the light to a detector for measurement. Here's a picture of our actual lab setup. One of the most important devices or components is this chopper. So this is a wheel that we spin. This kind of flashes the light going into the system. And that way on the detector, we can look for that flashing signal and help pick it up out of the noise to increase our measurement sensitivity. Some of the challenges in this setup are that we're trying to measure pretty low signals through our components. There's unfortunately a lot of loss going into and off of the chip. And in general, our signal is just not very strong. It's very difficult to measure also because midwave light is not visible to the human eye, and our materials are not transparent to any sort of visible light. So optimizing coupling without any visual feedback is pretty challenging. Here's a description of our waveguide loss measurements. So we use the cutback method to characterize our waveguide loss. So this involves structures that we call paper clips because they're kind of shaped like paper clips here. These structures all have the same number of inputs, outputs, and total bends, but have variable center lengths. So the components, when you plot the transmission as a function of component length, you can use the slope of that to give you your waveguide loss. So in the center here is a measurement of an air-clad rectangular waveguide, where we see a loss of about 1.7 dB per centimeter. And on the right, we have a silicon-clad rectangular waveguide measurement with a loss of about 3.6 dB per centimeter. For context, we're very happy with these measurements because our goal going in was about 1 to 2 dB per centimeter. There have been very few examples of rectangular waveguides shown in the literature. So this is pretty close to our goal loss that we're seeing here. And for silicon-clad, we don't know of any examples of germanium waveguides with top cladding in the literature. So while this loss is a little higher than our 2 dB per centimeter goal, we're very happy to have this number and improve on it in the future. Next, I'll talk about a different way of characterizing waveguide loss using ring resonators. Ring resonators consist of a loop of waveguide next to an input-output waveguide. When the light is going through this input-output waveguide, some of it gets coupled into this ring, and when the round-trip path around the ring is an integer multiple of the wavelength, you see destructive interference at the output. This leads to periodic dips in the transmission as you sweep the wavelength of your laser, shown in this figure here, which shows transmission as a function of wavelength. The shapes of these dips in transmission depend on the coupling into the ring resonator and also the round-trip path loss. So by comparing different ring resonator components with different coupling settings, you can back out what the waveguide loss is in your rings. So here's an example of an air-clad rib waveguide measurement using a ring resonator. So we see very narrow bandwidth filtering performance with a full width half max about 0.8 nanometers and an extinction ratio of 10 dB. This corresponds to an air-clad rib waveguide loss of about 0.6 to 2 dB per centimeter. This span of measurements has to do with the different wafers that we've measured. So this actually matches the state of the art for air-clad rib waveguide measurements at this wavelength, which is 4.6 micron. On the right here is an example of measuring for silicon clad rib waveguide. And again, we're seeing very good narrow bandwidth performance with an extinction ratio of 12 dB. And this corresponds to a silicon clad rib waveguide loss of about 3 to 7 dB per centimeter. Okay, so now I'm going to talk about some of our upcoming designs. We're in the process of laying out a new mask containing some new designs, which we're very excited about. The goal of this upcoming mask is to expand our passive component library by including new devices such as adiabatic couplers and polarization rotators. We're also updating some of our old designs based on our laboratory measurement results. Here's a floor plan of this overall mask containing a lot of different passive components. Something we're also very excited about is to include active components on this upcoming mask. So we're going to be demonstrating plasma dispersion effect modulators over here. These happen when we add extra positive dopants and negative dopants into our waveguide. And then the positive and negative charges kind of repel each other. And by adding an extra reverse bias to this, you can change the area where those charges are repelled. And that changes the total number of dopants that your light is exposed to, which changes the refractive index. So this is how we form a modulator in our Germanium-on-Silicon platform. This slide kind of summarizes the final status of our Midwave infrared integrated photonics platform. So we have a number of different passive and active components that have either been demonstrated or we're planning for the next mask. And this table intends to kind of map how these components relate to an eventual midwave infrared application. So how we could use these building blocks to kind of contribute to a more complex system level design. So the first component is a waveguide. This is probably the most important component because anything you do is going to need low loss routing of light. And at this point, we have fabricated and tested these waveguides in lab. The next couple of components are input-output tapers, which reduce the coupling losses, and rectangular to rib tapers, which allow you to convert between the two different waveguide types that we have. These have also been fabricated and tested in lab. The next component is a ring resonator. These are very useful for narrow bandwidth filtering, which is useful for a lot of optical applications. We also have adiabatic couplers shown here. This can split up light 50-50, or you can add light in the back and kind of combine light that way. This is useful for creating Mach-Zehnder interferometers or optical switches. We also have a polarization rotator shown here. This is important for source integration because we're planning to integrate a quantum cascade laser source. These laser sources tend to output in the TM mode, and so we use this polarization rotator to rotate it to the TE mode, so it's more compatible with the rest of our passive component library. For the active devices, we are going to be demonstrating modulators and thermal phase shifters. These are both very useful for changing the refractive index of light going through. So this can be combined with our other passive components to make optical switches or tunable filters. We're going to be integrating some quantum cascade lasers. This is going to be very useful because you could potentially miniaturize a transmitter for active remote sensing. So you could have a LiDAR, for instance, in this wavelength range, if you could make a smaller, more robust source. And finally, we have some test structures for photodetector integration. Having integrated photodetectors is very useful for on-chip calibration of your transmitters or for on-chip signal measurement. In conclusion, our Germanium-on-Silicon platform shows very promising initial results for midwave infrared integrated photonics. At 4.6 micron, we have measured waveguide losses as low as 0.6 dB per centimeter for air-clad waveguides and about 3 to 7 dB per centimeter for silicon-clad waveguides. The next steps for this project are to tape out this next mask and get these new devices fabricated and tested. We're also continuing with our top cladding fabrication experimentation and lab testing to see which top cladding fabrication approach is best. And in the future, we're going to be combining all of these different building block components that I've talked about today into a more complex system demonstration. So I'm happy to take any questions. Thank you very much for your attention.
Hey, thanks, Rachel. That was a great talk. It looks like Midwave is off to a wonderful start, and
Thanks.
you're anticipating the next set of results with lots on the masks that they're. When are those due out?
So the tape out is kind of ongoing, and we're hoping to be done at the end of the month. And then fab will probably take 2 to 4 months-ish.
Okay, so sometime late summer, maybe we'll have.
Yeah.
We'll have some.
Exciting.
Yeah, very exciting, very exciting. Okay, I guess we do have time for questions. I know there's been some questions in the chat and in the Q&A channel, so let me try to sort through these. Let's see, somebody asked the reference index on germanium in the midwave.
Yes, so we actually can use the free spectral range. I didn't talk about this specifically, but this free spectral range in our ring resonator measurements provides us with a pretty good measurement of our germanium refractive index. So at 4.6 micron wavelength, it's about 4.07. And these lab results indicate that we're within about 1% of the guesses that we had going in. So that's pretty good. Our designs are pretty close to what we anticipated.
All right. Someone asks, are there applications for your technology in the oil and gas sensor space, measuring sulfur, viscosity, etc.? I don't know how much.
Yeah, there's been different papers out about miniaturizing gas detection sensors, such as methane and things like that. It's a very interesting spectral region because there are a lot of different gases that have absorption features, and they tend to be stronger in the midwave than they are in the near infrared. So it'd be cool to be able to miniaturize in this wavelength range particularly.
Right. Let's see, someone asks, do you grow the germanium film at Lincoln or buy commercial germanium-on-silicon wafers?
Yeah, all of our fabrication is done at Lincoln Lab in the microelectronics lab.
Right, so we do have a germanium reactor, so that's very useful for what you're doing. I also asked, how do you couple the light from the laser to the fiber?
That's a good question. I have a picture of that here. So this is our fiber coupling setup. So here's our laser. This is an optical isolator. We have some mode matching optics here, and it reflects off of this mirror to this mirror. And then this is a collimator that we use to couple the light from free space into the fiber. And then from there, the fiber is launched here. The chip goes here. And then here's the output fiber that goes to the detector.
All right. Let's see. What is the thickness of the passivation layer, and which methods did you use to code it?
In here, I don't know that number off the top of my head, but my email is listed here. So if you shoot me an email, I can get that number back to you. Okay.
Okay. And I guess back on the previous coupling discussion, what kind of coupling losses do you typically get?
So for silicon clad, where we have input output tapers, we're seeing about 10 dB per facet. And then for air clad, we don't have input output tapers because it just doesn't really work with that geometry. So we see about 15 dB per facet, which is pretty high. So we're looking into ways to alleviate this going into the next mask.
Okay. Someone asks, many fabs fabricate germanium-on-silicon photodetectors for 155. Can we just use that process to fabricate germanium-on-silicon waveguides? What are the challenges? So I guess you're asking.
So the growth. Oh, sorry.
In terms of tech transfer to production process, that's straightforward, or?
Yeah, I think the growth is very similar. So we can use a lot of the same tools that are used in silicon photonics. So that's a major benefit of having CMOS compatible materials with this germanium-on-silicon platform. So a lot of the processes are very similar, and the tool sets we use are very similar. There's one of the main differences is that germanium is a lot more sensitive to chemical attacks, so it kind of complicates some of the processes. And yeah, I think, does that answer your question?
Yeah, I think the person asking the question was wondering whether you could directly use the existing processes that build germanium detectors and trick it into building waveguides. I guess it would be, yeah.
I guess that's sort of what we're doing.
Okay. Okay. Let's see, another person asks, did you find that the polycrystalline silicon cladding showed lower loss than the epitaxial silicon cladding?
The best performance we're seeing is with epitaxial silicon cladding, but we still have a lot of samples to kind of go through. But yeah, the epitaxial silicon has been performing the best so far in our lab measurements.
Okay.
So all
And,
of these lab results were epitaxial silicon, to clarify.
all right. And somebody asked about the germanium etch method in chemistry.
That is also a good question. I'm not really a fab person, I'm more on the optics side. So if you want to shoot me an email, I can give you some more details later on offline.
Okay. And then somebody asked if you measure the devices at other mid-IR wavelengths.
So far, all of our testing has happened between 4.3 and 4.8 micron, but in the future, we'd like to get more lasers. It's kind of a setup limitation at this point. Our laser goes from 4.3 to 4.8, so that's where I've been testing everything. But we do have plans in the future to expand to the shorter wavelengths.
Okay. And I guess I can't see raised hands, but I understand that there is somebody with a live question with their hand raised. So if you could just unmute and ask, that'd be great.
Hello, yes. Can you hear me?
Hi, yes.
Okay, yes. This is Juan Sommer from Killer Labs at Texas Instruments.
Cool.
Yeah. My question is about the dispersion effects. Okay, so you know, I don't know how important are dispersion effects for your applications, but in general, it's known that you know, when you have a high contrast in the refractive index between the core and the cladding, the dispersion effects actually could be important. Okay, so playing with these two things, you can minimize those dispersion effects. But I don't know if you're using a monochromatic signal here. Probably it's not important, but maybe for some applications, dispersion is worth to measure. Correct?
Yeah. So when we design these components, I kind of bucket up the wavelength ranges. So I'll have just like a set of waveguides. So one will go from like 2 to 2.5. It'll be the same waveguide for like 4.5 to 5 micron. So we have an estimate of what the refractive index is across these wavelengths. And then when I'm designing, I kind of account for that dispersion. One of the components that is the most broadband is an adiabatic coupler. And so in simulation, I have an adiabatic coupler. It goes from about 4.5 to 5 micron. So we haven't specifically measured this dispersion, but we keep track of the refractive index for each wavelength specifically during design.
Okay, we have built you know, a lot of waveguides for the millimeter wave application. Okay, so essentially much lower in frequency. Okay, and essentially it is key for the application to look at dispersion, especially if you're going to use it for communication. But you know, I'm just saying here, okay, that it will be important for the next time if you measure dispersion. Maybe that will be interesting results. Okay.
Okay. Yeah, that's a good idea.
Thank you. Thanks.
Okay, so I don't know if there are any other questions, live questions, but if there are, just go ahead and unmute and yell out, I guess, because I can't see raised hands here the way the setup is right now. So if not, maybe we'll do one or two more from the chat. Let's see. A lot of very detailed ones, but here's one. Do you think future improvements in integrated photonics would come from better designs or better fabrication material platforms?
That's an interesting question. I think probably a combination. I think the fabrication is going to get better and better. So as I was talking about, like these smooth sidewalls are pretty difficult to achieve and very pivotal for good performance optically. So I think just better materials and more experience will kind of improve that. Something that's getting pretty interesting is kind of the advent of inverse design. And at these wavelengths in particular, you can have kind of sub-wavelength features because the wavelength is so long that are within the fabricable limits of current processes. That's also a very interesting opportunity. So I think it'll be a combination. It'll only continue to improve, I bet.
All right. Well, maybe that's a great question to stop on. I know that there are some more in the chat. I think Rachel did give her email, so folks can, I think, reach out to you, Rachel, with
yeah, for sure.
So I just want to thank you again. It was a terrific talk, and I'm excited to see the next round of results, the end of the summer. So we look forward to that. thanks again to both our speaker and everybody that joined in. And until next time, take care.
Thank you for having me.